All right, the last section here, section 14.4, we're talking about mixtures and movements. First of all, let's talk about Dalton's law. Dalton's law is talking about if we have different gases mixed together. And it's often called the law of partial pressures. And what we're talking about is how much pressure each particular gas exerts in a container. And if you have all of these gases mixed together, let's say you have 3 gases in a container, each one of them is going to exert a little bit of pressure. You can add that up, and that's the total pressure in that container. So here's his law. P total is, pressure of the first gas, pressure of the second gas, third gas, however many you got, whether it's 2, 3, 4, whatever. You just add them all together. That's very basic. Makes sense. Okay, so if this one was 50, and this one is 100, and this one was 200, my total pressure would be 350. I'm assuming we're talking kilopascals. So here's Dalton's law of partial pressure says that once again we've got some constants here, constant volume and temperature. But what we're saying is the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of each of the gases that's in there. Let's take a look at a problem on page 434. All right, the sample problem says air contains oxygen, nitrogen, carbon dioxide, and trace amounts of other gases. What's the partial pressure of oxygen at 101.3 kilopascals of total pressure? So we know our total pressure, P total equals 101.3 kilopascals. We're trying to figure out the partial pressure of oxygen, which we don't know. If we know that the partial pressure of nitrogen is 79.10 and carbon dioxide, partial pressure of CO2 is 0.040 kilopascals, and the partial pressure of other gases, all other gases in here, is equal to 0.94 kilopascals. So here's what we know. We'll call we know that P total is equal to P1, which is oxygen, plus P2, plus P3, plus P4. So 101.3 equals, I don't know that one. That's the one I don't know. Plus 79.1 plus 0.040 plus 0.94. And if I add these up and subtract them, I get PO2 equal to 21.22 kilopascals. All right, why don't you try practice problem number 31. All right, it says determine the total pressure of a gas that contains a mixture of oxygen, nitrogen, helium, and here are the partial pressures. So PO2 was 20.0. Pressure of nitrogen, PN2, equals 46.7. And helium was equal to 26.7. Well, that's pretty simple. We're just going to, it's P total equals those three added together, so it's going to be 20 plus 46.7 plus 26.7. So 0.7. Okay. So add all those up, and what are you going to get? I don't want to think that hard. So plus 46.7 plus 26.7 equals 93.4 kilopascals. Okay, so you can see Dalton's law is pretty easy, pretty straightforward. All right, now let's talk about Graham's law, and we're not going to actually do the calculations, but I want you to be familiar with the terms and the information here. So first of all, let's talk about diffusion. We're talking about diffusion Diffusion is the tendency of molecules to move towards areas of lower concentration until it's the same. In other words, if I've got a whole bunch of things here, I'm concentrated, and then I've only got a few of them over here, these are going to kind of spread out and fill that room, or that container. They're going to spread out. That's diffusion. Now there's another term, similar, sounds similar anyway, called effusion. And this is where gas escapes through a tiny hole in its container, or tiny holes. And a great example of this is, think about when you blow air into a balloon and you tie it up and you let it sit there for days, and you come back and the balloon used to be this big, but after a few days it's kind of lost a lot of air. Well, that's effusion. That's the particles getting out through small holes in the rubber that they can fit through slowly, but they can eventually do that. And here's what's important to come away with this. Gases of lower molar mass diffuse and effuse faster. In other words, smaller things can get through the holes better. They move around faster. That makes sense. Think about, if you go fill a regular rubber balloon, you just blow it up, it's going to last a few days and get smaller. If, on the other hand, you take and fill it with helium is a much smaller particle, and those will leave a lot faster. So the helium ones will lose their air a lot faster simply because the particle is smaller. Now, if you want to combat that, then you go buy those Mylar balloons, which is made out of aluminum, and the holes in them are tighter. They're smaller than in a rubber balloon, so it's harder for the things to get out. All right, so here's Graham's law. It says that the rate of effusion of a gas is inversely proportional to the square root of the gas's molar mass. Now, like I said, we're not going to do any calculations with it, but just understand, once again, we're talking about the size makes a difference here. Smaller is going to get out faster. It's not going to be a straight line. It's going to be a curved line. We've got a square root, so it's going to be inversely proportional to the square root of its actual size. So smaller is not going to be, if it's half the size, it's going to get out 4 times as fast, basically, is what they're saying. And that brings us to the end of the chapter. You should be ready to take the test now.